Let's take a look at an example of a statement that lends itself to proof by contrapositive. For all integers a, b, and c, if a doesn't divide 2b plus 3c, then a doesn't divide b or a does not divide c. First, let's write the contrapositive. It will also be an if-then statement, and it will be universally quantified, as all if-then statements are. For all a, b, and c in Z, if, well, let's just think about contraposition. This is P, this is Q. And we're trying to write the contrapositive of if P then Q. So we're going to write if not Q, then not P. So the first thing we have to do is negate an or statement. De Morgan's law says negate each component and change the or to an and. So the negation of A does not divide B, of course, is A does divide B. Change the or to an and. And the negation of A does not divide C is A does divide C. So if not Q, which is what we have there, then not P. And the negation of A does not divide 2B plus 3C is A does divide 2B plus 3C. Let's recall the definition of divides. Okay, so we say A divides B, denoted by A vertical line B, if B is equal to AK for some integer K's. In other words, A divides B if B is a multiple of A. That means A times an integer. Here we're using K. So we want to prove the contraposition. Here's our proof by contrapositive. We're going to assume A, B, and C are integers. We always let our reader know where our variables live, their domain. And we're going to assume the hypothesis of the contrapositive. So we're going to assume A divides B and A divides C. We wish to show the conclusion that appears in the contrapositive. In other words, we wish to show that A does divide 2B plus 3C. We have our hypothesis, we have our wish. Now we apply the definition. The definition in play, of course, is divides. So by the definition of divides, we know a number of things. First of all, A divides B, so B is equal to A times K, where K is in Z. And, of course, since A divides C, we know C is equal to A times some other integer variable, let's call it J, where, of course, J is in Z. If we want to expound upon our wish, never a bad idea, we can realize that right before we can say A does divide 2B plus 3C, we have to have seen 2B plus 3C written as a multiple of A. In other words, we wish to show that 2B plus 3C is equal to A times M, for some m in z. So we want to say something intelligent about this expression 2b plus 3c. We want to show it looks like this, a times m. M, of course, won't be a single letter. It'll be an expression that we build from substitution using the equations that we have from our definition of divides. We'll also use closure properties of the integers to show that the expression looks like an integer m. Okay, so let's introduce 2b plus 3c into the conversation. I like to just say observe, and now 2b plus 3c is of course equal to 2 times b, which is a k, plus 3 times c, which of course is a j. And since we're trying to show a divides 2b plus 3c, we take a and factor it out from both terms. And we have a times the quantity 2k plus 3j. So we're halfway home. We've shown 2b plus 3c equals a times something, and that's going to be our big K, right? Or what we call m. It's an integer. Why? Well, because it's constructed from multiplying integers together. 2 times k is an integer, 3 times j is an integer, and then adding two integers. 2k is an integer plus another integer, 3j, will yield an integer. And so we simply say, since z is closed, under multiplication and addition, we see that, we'll call it m, which is this expression 2k plus 3j, is in z. So the expression of interest, 2b plus 3c, is equal to a times m, where m is in z. This means a divides 2b plus 3c, which is what we wanted to show.